given this problem cold, I would have no clue that Cauchy Schwarz inequality would even apply. But Cauchy Schwarz is a powerful, it's a pretty powerful inequality because it holds for all real numbers, in fact, all complex numbers. But for all AI, BIs that are members of the real numbers, this holds. Let me do better than that, please. Okay, for all A sub I, B sub I, 1 through n, they're real numbers. They're real numbers. That's what was left out right here. Now, if you're given the Cauchy Schwarz inequality just in your face like this, you can kind of see why it might work here to establish this truth right here. But it's not altogether clear until you actually write out some things. Like when you write out P evaluated at xy, you just take an xy, you take xy and put it everywhere you see an x, and you get this statement here. And all of a sudden you realize that you can split this up using Cauchy Schwarz. In other words, this would be your, as far as the formula goes, this would be A sub 1, B sub 1. It's very, very mechanical, very little intuition, or at least I have very little intuition on something like this. Very mechanical process. Now this is A sub 2, B sub 2 right here. And then, of course, A sub 3, B sub 3. Now, if you don't have any experience with this, it's you can think this is a vector where this is an inner product of an n-dimensional vector. And it says the inner product of that n-dimensional vector is equal to the product of the square roots of the magnitudes, or the products of the magnitudes, I guess, excuse me, is how you would say that, okay? But it does have an interpretation in terms of vectors, all right? But anyway, with these assignments, the Cauchy Schwarz inequality works quite nicely. You can just see straight up here, this line right here follows immediately from this Cauchy Schwarz. Some people just call this CS. This particular citation here just called it Cauchy's, but CS a lot of times for Cauchy Schwarz, sometimes Bunyakovsky, I think. But in any event, this is just a very direct application of this inequality right here. You can see that this guy right here would be A sub 1 quantity squared, as far as, let me write this out, A sub 1, as far as this assignment right here, this would be A sub 1 quantity squared. And so you can kind of see how you're just following your nose here as far as writing this thing down. You're not, it's just a very transcription sort of thing, not really a lot of insight going on, okay? Now, because we're trying to show that P of xy quantity squared is less than or equal to P evaluated x squared times P evaluated y squared, it makes sense to square both sides, okay? And so that's what we do. We write this down, squared both sides, and when you square this side, the radicals just go away. Now notice, though, that this piece right here, just by construction, would be P at xy, P evaluated xy, quantity squared, the entire image of the polynomial under xy squared. Okay, then this right here would be P at x squared, just like what we're trying to show, believe it or not, okay, times P at y squared. Okay, folks, and again, that was what we were trying to show. Again, this is not the best problem, and I would have had no idea to even apply Cauchy Schwarz had I not looked at a solution. But anyway, we were trying to show that P of xy quantity squared is less than or equal to P of x squared times P of y squared for all real numbers. And we've done that right here. This part is exactly P of xy quantity squared, and this is P at x squared times P at y squared. And again, that's easy to see when you just, where do we do this? P of x is equal to ax squared plus bx plus c, right? And so if you put an x squared there, you get x to the fourth, you get x squared right there, which is what we're doing right here with the variables x squared and y squared. Now, one thing you may wonder, why did we restrict the integers? It's just as simple as we restricted the integers to be greater than or equal to 0. And that's because we had to take the square roots down here, right? That we can't have the square root of, just for example, right here, you can't have the square root of a negative number, right? So you have to, we're assuming that the A's, the B's, and the C's are non-negative integers, right? You can't, the square root of a negative number is equal to I, and you can't order the imaginary or the complex numbers as far as I know, okay? So anyway, y'all, we've completed the proof. And again, this was a Russian Math Olympiad all the way back in 1997. It was the first problem. And I'm pretty sure it was an RMO. I found this document on the web that talked about the 23rd Russian math competition. And it didn't use the word Olympiad. But anyway, this is the RMO. As far as I know, it's RMO all the way back in 1997. Okay. Thank you for viewing.